It is Monday. This is going to theoretically be a full 5-day week with everybody here.
I'm gonna check the weather real quick.
Yeah.
I feel like
I already have. It's supposed to be like 60 to 70 every day.
I feel like we can change that.
And so the only hope is Thursday. There's supposed to be some rain coming in. Maybe it'll be like, a threat. Not really a tornado, but the threat of a tornado. And, but we'll see. I don't know. The powers of the universe have figured out unique ways to make sure that we don't have school all the time, at least in a normal way. So we'll see. But we have, we're closing in on the end of February. Am I on?
Yes.
Closing in on the end of February, going into March. Okay, we're finishing up this equilibrium. Again, in a utopian world that will be finished today. This week. I do want to do a lab on Thursday. So as you're planning your sleep-in mornings and days you need mental health, because by Thursday you're going to be tired, don't miss Thursday morning, okay? Because labs are a royal pain to try to make up and do, okay? So lab on Thursday. I don't think that will be enough time for us to have a test on Friday, but it'll be probably at the beginning of next week. We will be having our comprehension survey regarding equilibrium. And so what we have left is we've finished all of chapter 15, and now we're going to go into the back half of chapter 17, talking about a different type of equilibrium called KSP, with SP standing for solubility product, not spinning part, okay? So solubility product, there's going to be 5 types of problems of these, and the last two will probably end up being bonus, because I don't think they're on at least the last one for sure is not on the AP test anymore. And I'll double check to make sure. I don't think the last two are actually still on the AP test. We'll just look at the 3 main ones. All right, so equilibrium, let's just go solubility product. Solubility product. We're going to call it KSP. Now again, K is K. Doesn't matter what the subscript, whether it says KEQ, KP, KC, KA, KB, KSP. Doesn't matter what the little subscript is. It's the equilibrium constant K, so it's products over reactants, and we only put aqueous and gases into the equilibrium expression. That's an always, so it doesn't matter what the subscript is. It's always going to be products over reactants, coefficients raise the powers. Okay? So the first type is calculate the molar solubility given KSP. Molar solubility, what do you think that is? Okay, the amount that's dissolved. Okay, but what units do you think? Molarity. Okay, when we want molar solubility, that just means what's the molarity. Okay, now, if I was to go and I was going to mix silver nitrate with, if I just said silver nitrate plus sodium chloride, what's that going to make? Silver chloride plus sodium nitrate. Now I know that this is aqueous, so if a reaction is going to occur, I have to have either a solid, liquid, or a gas forming. And if you look up here on our solubility chart, you see the chlorides, actually all of the halides, chlorine, bromine, and iodine, are soluble with most things, but form precipitates with silver, lead, mercury, and thallium. So this is gonna be my precipitate. That's a very common precipitate. So up until this point, we've always said, okay, well, it's insoluble in water. But if you look again at that solubility chart, it says solubility less than 0.1 molar. That just means it's not very soluble in water. Doesn't mean it's completely insoluble. Nothing is completely insoluble in water. It's just not very soluble. So most of it precipitates out, an itty bitty little bit stays in solution. So we can go and we can look at the KSP value, and you go and you look in the table in the back of the book and your aqueous equilibrium constants. Maybe, not for sure. Solubility product constants. Here we go. Page 1104 gives you a table of KSP values. So I go and I find silver nitrate. Pretty much know what it is, but I'm making sure. I'm not silver nitrate, silver chloride. And it's 1.8 times 10 to the minus 10. So if I look at AgCl solid, it's actually going to be in equilibrium in that solution and look like this. And the KSP is given as 1.8, 10 to the minus 10. So when we do this reaction, we say, okay, so chloride's precipitated out. Most of it is going to be precipitated out. Notice 10 to the minus 10. What does that mean about the position of my equilibrium? Going to be product or reactant favored? Very reactant favored. So in other words, most of it is like this. Only an itty bitty little bit is like this. So the majority of it is indeed precipitating out. But with KSP, we want to say, well, how much didn't precipitate out? How much stayed in solution? And so we always write the equilibrium for the precipitate, okay? AgCl. So again, if I'm going to do KSP, 1.8 times 10 to the minus 10th, what's that going to equal? What's my KSP expression going to be? Yeah, come on, we've been doing it for a week. Now, do we include this one? Why? It's a solid. Okay, so we got to pay attention to the state, so we don't include that because it's a solid. So it's just going to be this times this. What this means is that the silver concentration times the chloride concentration, when they're in solution, that product cannot exceed this amount. Anything over that amount is going to precipitate out. So this is going to be pretty simple calculation. What do we plug in for this and this? X and X. So it's going to equal X times X, or X squared. So the square root of 1.8 times 10 to the minus 10 is equal to my silver concentration, which is also equal to my chloride concentration, which somebody gave me, what's the square root? 1.8 times 10 to the minus 10.
1.34 times 10 to the negative 5.
So if I mix, it doesn't really matter how much I mix. A bunch is going to precipitate out, and this much of each ion is going to stay in solution. Okay? Now, one of the last two types of problems is, will a precipitate form? And we're going to look at this. If I put silver nitrate in and I put sodium chloride in, if I know then this is going to 100% ionize, this is going to 100% dissociate, this is going to be 100% dissociate. If I know what the silver ion concentration is, if I know what the chloride ion concentration is, given the KSP, I can tell, is it bigger or less than KSP? If it's greater than KSP, a precipitate is going to form. If the product's gonna be less than KSP, no precipitate will form. This is just telling me what's the maximum amount of each ion that can be in solution. Okay? If we just do another example, magnesium hydroxide. What's that? And this, did I do equilibrium? Yes. What's this going to dissociate into?
Mg2 plus and 2OH minus.
Okay, so that's how it's actually, you're going to put this into water. A little bit's going to break apart. Hey, and advice right there, turning that, just turn that around, find magnesium hydroxide. What's the KSP?
1.8 times 10 to the negative 11.
That 1.8 seems to show up a lot on these K values. I don't know why. I have no earthly idea, but there's a lot of ones that have 1.8. So this time, to find what is the molar solubility, 1.8 times 10 to the minus 11th, what's my equilibrium expression going to be on this one?
Mg2 plus multiplied by 2OH minus.
Well, it's going to be OH minus
Squared.
Okay? I mean, it's just, again, solids are ignored. So in KSP, we're only going to have the products. You're never going to have a reactant on a KSP problem. Because the reactant is always going to be a solid. We're trying to decide how much of this is actually soluble. We do this for the things that are nearly insoluble. Because if it's very soluble, like a nitrate, where you're going to have almost all product and no reactant, and you're going to have super large, you're going to be approaching infinity with the value of K. So we're only going to do KSP with things that are limited solubility. So what do I put in here? X and, well, but the concentration of this one's going to be double it, isn't it? So the 2 is going to play twice. We're going to say 2x squared. Because the X is representing the concentration of magnesium, so the hydroxide concentration is going to be double plus U squared. So obviously in your high level math, 4x cubed. So we go 1.8 times 10 to the minus 11th divided by 4, and then we take the cube root. Now in this case, the x is only going to equal my Mg2 plus. We're all good with the algebra, right? Now to make sure you know how to do cube root on your phone, on your calculator, which might be one and the same. And somebody's getting me a value.
I got 1.65 times 10 to the negative 4.
Okay, so my OH minus is going to equal 2 times 1.65 times 10 to the minus 4 is equal to 3 point, how come I can't do that? 3.3?
Yeah.
Okay, so to determine the molar solubility means how much is actually dissolving based upon the KSP. We just write the equilibrium expression for the dissociation of the precipitate, knowing that only a small amount of it's actually going to do that. And then we just plug in, if it's 1 to 1, it's just going to be x and x. If it's 1 to 2, it's going to be 1x and 2x. If we happen to do aluminum chloride, AlCl3, well, I'm not sure aluminum chloride is a precipitate, it's not. Let's say we do Let's say it's aluminum sulfide. This will be even more complicated. Aluminum sulfide. What's that one gonna dissociate into?
2AL.
2Al with a 3 plus. Because remember, ionic compounds dissolve as ions, so we have to put the charge. It's not just going to be Al, because aluminum doesn't dissolve in water. Aluminum ion will dissolve in water. You put aluminum foil into water, it doesn't dissolve. Okay? You put water into an aluminum pot, it doesn't dissolve. Okay? But when it does go into solution, it's going to go in as a +3, and what's the other one we're going to be?
3 S2 minus.
S2 minus. Okay? Now, is aluminum sulfide even on there?
No.
Yeah, it's not common. Somebody get your phone out and say, hey Siri, what's the KSP for aluminum sulfide? Zoe's got it. She doesn't want to ask Siri though, she's just typing it in. What is the KSP for aluminum sulfide?
You don't know this by heart?
I'm sorry.
I'll tell you that, it's probably 1.8 something.
It's not coming up.
Alright,
So it's 2 points.
I got a good guess.
Times 10 to
You
the
got a good
negative
guess.
11.
1.8.
Nobody's finding it?
To the negative 12.
It's come up with a bunch of worksheets, and I was like,
2.7 times 10 to the negative 11 is what it is.
No?
let's just stick with
Truth tell you, you're not
1.8.
getting it?
I got 2.02, but it doesn't give me a 10 to the power of anything.
Let's just say.
1.8.
Okay. The number is irrelevant in this as far as what I want to point out. So what did you, 2.7?
Yeah,
What was your guess?
2.7 times 10 to the negative 11.
I think it's going to be more like 10 to the minus 18.
Okay.
Okay? Now, I'm going to put it at, this is an estimate. All right, so don't hold me to that one. But that's irrelevant. What's the KSP expression going to be?
AL3 plus squared times S2 minus Q.
But what would I put in then for X?
2L, 2X squared.
So we're going to say 2X squared,
Then 3x.
3X cubed. So then you just got to go through and do all that. Now that's pretty rare. Usually it's going to be one of these two. Okay? But it could be something crazy, but it's going to be the same thing. You just do it no matter what. Okay? So we don't have to solve this because this one number is probably not right. Well, probably not right. I can pretty much guarantee it's not right. Okay? But this is how you set it up. Okay? So then it's going to be 4x squared times, 27x cubed. Okay? And multiply all that out. So you're going to have x cubed and x squared is going to have x to the 5th. 27 times 4. So 5,408. X to the 5th. Okay? So that's the first type of problem. Pretty straightforward. Now, again, molar solubility, that's going to be the key, is what you're going to look for in the problem when it's asking the question. What is the molar solubility of some compound? And they give you the KSP. As soon as you see KSP, you need to be thinking, okay, well, the precipitate is what they're asking about. The precipitate, you always write the equilibrium in terms of the solid dissociating into the ions. All right, so the second one is just going to be the reverse. Calculating KSP given molar solubility. Okay, now if we look here, this is where I'm going to get one out of the book because I can't make these up. That's 18, chapter 17. Okay, I'm gonna be on page 770. $770. And if we look right here at, I think it's right on the one I want, number 59. Shoot, I just wrote all over the wall. It says, consider a solution no, that's not the one I want. Molar solubility is, there it is. That's the one I want, 53. Okay, if the molar solubility is this, what is KSP at that temperature? And again, K is always temperature dependent. Okay? So notice it's saying you're given molar solubility looking for KSP. So I'm going to say I want calcium fluoride. What's that going to dissociate into? Ca2 plus how many? 2. All right? So we want to calculate KSP. Now they tell me that the molar solubility is 1.24 times 10 to the minus third. Okay? That's how much actually dissolves. But remember, ionic compounds, none of it's going to dissolve like this. It's all going to dissolve like this. So, if this is how much dissolves, what's my calcium concentration going to be? Same thing, 1.24, 10 to the minus third. What's the fluoride ion concentration going to be? Twice that, 2.48 times 10 to the minus third. So to calculate KSP, it's going to equal calcium 2 plus times F minus squared, which is going to equal 1.24 times 10 to the minus third times 2.48 times 10 to the minus third squared. That's all there is to it. So what we get? Some of y'all might need to really practice putting all this exponents and stuff, the scientific notation you're, into your calculator. It's been a while since you've done scientific notation. Anyone with a value?
7.63 to the minus.
Say it loud enough for me to hear.
7.63 times 10 to the negative 9.
Does somebody agree with that number? Okay? So we'll go with that, 7.63 times 10 to the minus 9, and that's going to be my value of KSP. So the first two problems are calculate the molar solubility or KSP. Either way. So if I look now at B on this one, it is found that 1.1 times 10 to the minus 2 grams of SRF2 dissolves per 100 milliliters of aqueous solution. Calculate the solubility product. Solubility product, that means KSP. All right? So when it says calculate the solubility product, that means find KSP. What's the only thing we're gonna have to do differently here? We have to convert it to molarity, okay? So we have this many grams per 100 milliliters. So it is 1.1 times 10 to the minus 2 grams of SRF2 per, I'm just gonna go ahead, I know it's got to be in liters, but just change that. So what do I have to do grams? Use the molar mass and convert to mole. So strontium is one I actually don't have a clue as what it is. 87.62 plus, we'll go with 38. So 38 and 87 is 117, 125.62. Somebody adding these together? Yeah, but I did 19 times 2 is 38.
Oh.
Okay, so 38 and 87.62. Should be 125.62. So I'm gonna say 1 mole over 125.62 grams. Grams will cancel, that leaves me moles per liter. So this divided by 0.1 divided by 125.62 equals, or you could do 1.1 times 10 to the minus 2 divided by parenthesis 0.1 times 125.62, close the parenthesis. But again, you guys need to practice putting all this in your calculator because you don't want to set it up right and then miss it because you're not putting your calculator correctly. Okay, so what do we get for this? What do we get for this one? For the molarity? Come on, y'all.
8.76 times 10 to the negative 4.
10 to the minus 4. Okay, so that's my molarity. So what's my strontium concentration actually going to be? The same thing, right? What's my F minus going to be? 2 times that. Okay, so when I do KSP, it's going to equal 8.76 times 10 to the minus 4 times 17.52. So 1.752 times 10 to the minus 3rd squared.
$2.69 times 10 to the negative 9.
And that's your KSP value. Now the reality is we don't worry about units, but what would the units be on this? Not squared, cubed. Molarity and then molarity squared, it's going to be molarity cubed. Now, rarely do we have to worry about putting the actual unit, but it's just going to be the molarity of those. So when you look at C, what type of problem is C?
First
It's going to be like this one, right? So go ahead and see if you can just do that in your notes. this current rate, we might get through all of these today, and then we'll do practice problems tomorrow. Princeton review on Wednesday. Lab on Thursday.
Review Friday.
Although, say let's slow it down.
Well, we'll see.
Second lab on Friday.
Quinn, it's like Mr. Grady's class.
Mm-hmm.
Lab every day.
We had 7.
I think we were in the lab more than the classroom.
So what is my equilibrium expression going to equal here? KSP is given as this. What do I put to the right?
BA 2 plus
BA 2 plus
times IO3 to the second power.
squared, right? Now, before we even go on, IO3 minus. What's going to be the name of IO3 minus? Well, it's not on any of our ion charts, but how can I figure it out? Iodine's in what family? Halogens. What do we know about elements in the same family? Why are they called a family? Similar properties. Okay? So I look up here and I can see that chlorate is ClO3 minus. So what's IO3 minus going to be? Iodate. Okay? What would BrO3 minus be? Bromate. Okay, so we can, if we know one, we know the whole family. So IO2 minus would be iodite, IO minus would be hypoiodite, IO4 minus would be periodate. Just like the CLs are all the same thing. If you know chlorine, you know bromine, you know iodine. They all do the exact same thing. So just in terms of naming, we can just kind of, sometimes we can get intimidated on a problem by the name. So what do I put in here then? 6.0 times 10 to the minus 10 is going to equal x times 2x squared equals 4x cubed. Divide by 4, take the cube root. So X is gonna equal
5.3 times 10 to the negative
4.3?
4.
5.3 times 10 to the minus 4th molar. That's going to equal my barium concentration. My iodate concentration is going to equal 2 times that, which is going to be 10.6, so 1.06 times 10 to the minus 3rd molar. But the question asks for what is the molar solubility of this? So if which one of these is going to be the same as that? The barium, right? The one that's 1 to 1. So the molar solubility is going to be this value. It is equal to the molar solubility of your BaIO3 2. That's really what we're interested in. Okay? Because for every one of these that dissolves, you get one of those and 2 of those. So when we find this concentration, but know that that's actually how much of this actually dissolved. So the solubility is always given in terms of the reactant. So when it says the molar solubility of such and such, it's always going to be of this part. And then you got to figure out those parts. Are we good with this so far? None of it's been super heavy duty? K is K, products over reactants. Let's look at the third one. Calculating the molar solubility in a solution containing a common ion. KSP is given. So let's look at 57. Using Appendix D, that's where advite is, calculate the molar solubility of AgBr in pure water. That's just, oh, he's not here. Okay, that's where he's going to be. Okay, using Appendix D, calculate the molar solubility of silver bromide in pure water, okay, which is what we just did. So we would say, so number 57, okay, this is going to be silver, it's silver bromide. Going to dissociate into Ag plus Br minus. So, going and we look at the KSP value for silver bromide. Say that one more time. 5.0 times 10 to the minus 13th is going to equal x times x. So just take the square root of that. X is equal to the Ag plus, which is going to equal to the Br minus, and it's all 1 to 1, which means the real question, AgBr, and that's all going to equal, just take the square root of this, Okay, so that's the solubility of silver bromide in pure water. But now, on B, it says, in a solution that has 3.0 times 10 to the minus 2 molar silver nitrate. So now, if we do like an ice table, initial, okay, we put this in as far as what it says, well, I calculate the molar solubility. We have this much in 7.07 times 10 to the minus 10th, okay? Well, let's just say we have X amount of this and we have X amount of that when we put it in, which turns out to be this much. But if I have it in a solution of silver nitrate, what else am I going to have present? I'm going to have some more silver, okay? I'm going to have 3.0 times 10 to the minus 2 molar. So that's going to be my initial concentration of this, but then I'm going to get some more to go in. So when I do my KSP, 5, 10 to the minus 13, I'm going to have 3.0 times 10 to the minus 2 plus X times X. Because I have silver coming from two sources. I have the silver nitrate that was in the solution to start with, and then I'm going to get a little bit more silver coming from this. Now, solubility product says that this times this cannot exceed this, so as this number gets bigger, what has to happen to this one? It's got to get smaller. And I'm going to write this down in a second, but adding a common ion always lowers the solubility. Because as the common ion goes up, the amount of the other ions that go, X has to decrease in order to do that. Now, for the first time ever, significant figures are going to be your friend. Because of sig figs, because X is going to be very tiny because of this 10 to the minus 13, 3.0 times 10 to the minus 2 plus X, for all practical purposes, is still going to be 3.0 times 10 to the minus 2. So we assume X is negligible. Assume X is negligible, so then we're going to say 5.0 times 10 to the minus 13 is equal to 3 times 10 to the minus 2. Now this X, we're looking for it. We don't negate that one. I mean, we don't just make it go away. We're looking for how small X is. But X is negligible, so 3.0 times 10 to the minus 2 plus X just equals that. I'll go ahead and write that over here. Still approximately equals 3.0 times 10 to the minus 2. That's what X negligible means. So now the math is actually it's a lot easier. Now we just go this divided by this. 5 divided by 3 is equal to 1.67. And it's going to be times 10 to the minus 11. Did I do that right? So that's X, and I let X equal the bromide, so that's really going to be my solubility now of AgBr. Notice it went from 7.07 times 10 to the minus 7th down to 1.67 times 10 to the minus 11. It's called a common ion. Solubility, whenever you're dissolving it, it could have been either one of these two ions being common. As the common ion goes in, it lowers how much of this can come in from the silver bromide. Okay? So this is where I would write right here underneath. I don't have room, but I'm just going to say it. The solubility is always less when a common ion is present. The solubility is always less when a common ion is present. So if you need things to precipitate out maximum amount, you don't precipitate them out of pure water, you find a common ion and you precipitate it out of a solution that has that common ion, because even less is going to be soluble. All right, so we'll do a couple of practice problems with this right after the break. And then we'll look at our last two, and I'm going to go over those quickly because they're going to be bonus. At least the last one will be bonus. All right.